Going to start out by drawing an example parallel circuit. Like so. We'll label these 10 volts. I like to use fairly simple values. 20 ohms, 20 ohms, 10 ohms, 10 ohms. And I want to look at the observations that you've made in your notes. So last time when we talked about series circuits, we had 3 rules, one for voltage, one for current, one for resistance. We're going to do the same sort of thing this time. Let's look at, I'm going to say rule 1 on resistance first. So this goes to the analysis part, where I asked you to use your battery voltage and battery current to determine the total resistance using Ohm's law. What can you tell me about the resistance then as you go down that table? What do you see? Yeah.
Resistance numbers
They keep going down, don't they? Mm-hmm. And in fact, so if you were, it didn't matter if you did this, but if you did, just add one next and you kept all of the resistors you had in front of them. So for everyone, I started with a 20 ohm and then I added a second 20 ohm, but I kept these 2 and then added a 10 and then I kept these 3 and added a 10. What you'd see is that your resistance actually goes down. You could say even more. If you look at the resistance, not in the first one, but in every other one, can you tell me, is there some limit? This one's a little harder to see. There's a limit to that resistance even. Can you tell me anything more specific about the value of those of the total resistance compared to the resistors you have in the circuit? Do you have an observation, Jeremy?
Isn't it just all the resistances added up together?
Is that what Ohm's law tells you? Because Emily just said it went down each time rather than going up. I was adding a resistor each time, but the resistance keeps going down if you use Ohm's law to do it. Another thing you probably, if you look for it, you will note, is that the total resistance is always less than any single resistor in there, which now looking back you can probably confirm. And I'm going to put that down as our first rule, that the total resistance in a parallel circuit. So I'd say title this as parallel circuit rules or something like that. And I'll describe why with an analogy in a moment. And I'll say then the smallest branch resistance. And to understand why, consider this like a shopping center. So you go to Walmart or you go wherever. And these are the checkout lanes, and you're the electron. You and the other shoppers are the electrons. Let's say, for an example, that we don't have anything connected here. So these are actually gone. You've got 2 lanes, both of them reasonably fast checkers. They're decent. But now a 3rd lane opens, and let's say, for the purpose of this example, that it's a slow, let's say I put it 60 ohms, a slow checker. Well, compared to having 2 lanes, Even that slow checker allows a few more people to get through in the same amount of time, right? So it lessened the overall traffic, even though it's slower. And you could put somebody that does half as many as these, but it still speeds up overall. The same thing is going on with our circuit. Having an additional branch gives electrons one more way to go from the negative back around to the positive. They're only going to choose one of these, just like you're not going to turn around and go through another checkout line and pay again. Electrons can only go through one of these branches. So they kind of get here and they sort of have to make a choice. And this is just all governed by the forces pushing them along. But they could go through this branch or they could continue on. At which point here they could go through this branch or continue on, and then they'd have to go through here. But once they're to the other side, they've just got a wire going back. So they all travel along that wire. Having anything out here of any amount is better than having nothing. That's rule one. We'll talk about how to find the numeric value in a little while. Rule two, voltage. What can you tell me about the branch voltages that you measured? We're going to get somebody else thinking on it. And thank you, Jerry. And as necessary, I shall consult the dial. So that if no one wishes to volunteer, they can be voluntold. Anyone like to volunteer? What do you notice about all the branch voltages? Yes?
Don't they all add up to the total?
They do not.
Well, 10, 20, 10, 60.
Those are the resistances, and we already talked about the resistances. They do not add up to the total. I'm talking about when you measure the voltages. Look at your branch voltages, and what can you tell me about them? We're going to get someone other than Jeremy or Miss Sellers. Thank you both for volunteering. Zach.
Oh my.
No, look at your data. This one's actually really obvious. Look at your data. What can you tell me about your branch voltages?
They're really close together.
They are. They're practically the same. Is there anything else that they're practically the same as?
No. The current maybe?
No. Yes. The battery voltage too. And in fact, all of these voltages are the same. Whenever we draw them up here, we assume that we have perfect wires, which means the wires themselves don't have any resistance. When you measured it, you're using real wires, so you see maybe a little bit of a difference, but not too much. And in fact, if you look at this, the battery is connected just by wires to that one, and it's connected just by wires to this one, or that one, or that one. So really, all you're doing when you put a voltmeter across these two is connecting through these blank wires, through these plain wires back to the battery. So naturally, you're going to get the same voltage as this. And in fact, the rule that we use here is that all branches and the battery have the same voltage. The battery supplies it as usual. So there we're measuring the supply of energy, if you want to think about that. But each electron in our circuits are only losing that energy in the one resistor. So if we measure the two sides of the resistor, we're measuring it that it's losing that much. The third rule is about current. What can you tell me about currents in this one.
Is it the same throughout?
Is it the same throughout? Did you measure it to be the same throughout?
The resistor currents we did?
All the resistor currents are the same.
Pretty much, yeah.
Are all of the resistors the same?
No?
Then I don't believe you. Caleb.
All of the resistor currents are the same, they add up to the battery current.
All of them do add up to the battery current. Now, if I have the same voltage across these, they're not going to be all the same. They might be kind of in the ballpark, but some might still be twice as much as others. But they do all add up to the current coming out of the battery. So the branch currents add up to the total or battery current. And the reason for that is that if you've got current coming out of here, here's I, and we have our resistor 1, resistor 2, resistor 3, and resistor 4. Some of it's going to branch out here and become become current in this branch. A lot of it will continue on. Some of it will go down here through that resistor. Some of it will continue on, and then it'll branch again at this point. So what you were doing in lab was measuring how much was coming out of the battery. I'll put a little T for total there. And then you were measuring each of these individual branches. And they should be different based on resistance. If you had a higher resistance, it should be a lower amount of current. But when you add up all of these, they have to add up to this, because that was the source before it started branching. And then they come back in and join up on the other end and go back to the battery. All of those electrons have to make the round trip. Or maybe not those individual electrons, but the same number of electrons. So we'll take another look at data after this and see if we can figure that out. But let's, for an example purposes, let's do some of the math that you'll be working on the homework as soon as you finish this lab. So let's take a look at the different things I might ask you. As before, V1, V2, V3, or I2 or I3, whatever it is, those all refer to the branch. The number refers to the branch, or which resistor it is. We've got all of our diagram up here. So using our three rules, what can you tell me about the voltage of resistor 1 in my diagram? Look at the rule. All branches and the battery have the same voltage. Sophie.
Well, is it 10?
It is. How do you know?
Because it's the same?
Because it's the
battery?
same. You'll probably find a lot of this fairly simple. What can you tell me about the voltage drop across resistor 2? Kenna. Let's look at our voltage rule. All branches and the battery have the same voltage.
Mhm.
Yep, so it's how much?
Mhm.
10 volts.
How was ours?
Drew, how much?
10.
10
Voltage.
10 volts, yeah.
Yeah.
Lane,
I'm guessing 10 volts. I might be.
are you guessing or are you confident?
I'm confident.
Okay. Yeah, all of those branches have the same. So whether the battery says it, or if I have enough information to figure it out on some other branch, they're all going to be the same. How would I know how much current, how would I figure out how much current is going through that first branch?
You could look at rule number 3.
How does rule number 3 help me? I don't yet know how much total current is coming out, do I? Darn it!
No.
Yep.
Oh, it's not.
It would be, so the Ohm's law is V equals I times R. So that maybe that would be V divided by R.
If I want to find a current, I would take a voltage divided by a resistance. If I'm looking for the branch 1, I need the voltage in branch 1, which I just figured out, and the resistance in branch 1, which I already knew. 10 volts over 20 ohms. Okay. Yep.
Got that.
How about branch 2?
Well, it's 0.5 again.
Why?
Because it's 20 ohms for the resistance again.
So we take V2 over R2, right?
Yeah. So it's 10.
10 volts over 20 ohms again. What about I3?
Very good question. Then 60, or 10 divided by 60.
V3,
That's
which we know is 10
0.16.
volts, over R3, which was 10 ohms. Sorry, 60 ohms. 10 volts over 60 ohms, which is about 0.16 amps, a little less, but we'll round it. I4, that was a resistance of 10 ohms. So 1. So we can do that one in our head, R4.
Oh, yeah.
10 volts over 10 ohms gives me 1 amp. So, how much total current do I have? Add them up, right?
Oh, yeah.
0.5 amps plus 0.5 amps, that gives me 1. We have a 1 down here, so that gives me 2 plus 0.16 amps gives me a total of 2.16 amps. Okay, now the last question you might have to figure out. The last one, you have to do all of the rest to figure this one out. How much total resistance is in there? How would I even know? Does that work?
No.
What else? Just like you did in the lab. We just figured out we know the voltage coming out for the battery. We just figured out the total current coming out of the battery. So just like in the lab in the analysis, if you take the voltage of the battery divided by the current coming out of it, which we called total, that's R equals V over I, Ohm's law. So we had 10 volts over 2.16 amps. Gives us 4 point something.
4.63.
4.63 ohms.
Oh, yeah.
Less than any other branch. Because they've got so many more paths to go through, the total is actually less than any of its parts. What I want you to do now is think of these rules and what we've discussed to